All right, Chemistry 3101. This is Chapter 7, where we talk about alkyl halides and nucleophilic substitution and elimination reactions. And we're going to see a lot of alkyl halides in this chapter. Now, hopefully you know what a halide is. You should know what the halogens are. Right? The halogens are fluorine, chlorine, bromine, and iodine. Those are the halogens. If they have a negative charge, then they would be halides. So we have chloride, bromide, iodide, and fluoride, of course. Now, in terms of alkyl halides that we're going to look at in this chapter, we're going to look mostly at chlorides, bromides, and iodides. Fluorides will come up from time to time, and there's a good reason why we look at chlorides, bromides, and iodides more. But again, going into some details on what an alkyl halide is, if you have an sp3 hybridized carbon and you have a halogen attached to that, that is an alkyl halide. For example, if you had, just something simple like CH3Br, like that, we call that methyl bromide, but that's an alkyl halide because there's a halogen attached to an alkyl group, which just happens to be a little methyl group in this case. Now, outside of alkyl halides, we can have aryl halides and vinyl halides. This is, you see where we have a halogen attached to an sp2 hybridized carbon. These are not alkyl halides. These are aryl and vinyl halides, and these are not going to come up in chapter 7. They're not going to be the focus of our attention in this chapter. Substitution reactions involving aryl and alkyl halide, or aryl, and vinyl halides are covered in chapter 28 of our textbook. If you're the kind of person who has an inquiring mind and can't wait to get ahead, feel free to read that chapter, and you'll find a whole plethora of information in there about aryl and vinyl halides. But again, we're going to focus on alkyl halides. All right, so getting back to this whole concept of substitution and elimination. If you're like, well, I understand the words, but what do they mean in organic chemistry? Well, an alkyl halide, and this is just a quick representation of an alkyl halide here. In organic chemistry, oftentimes for a halogen, we just use X, and X will equal chloride, bromide, or iodide. So if we have an alkyl halide, just like we do here, and we have a nucleophile, and we discussed nucleophiles in chapter 6, if we substitute the halogen for a nucleophile, we call that a substitution reaction. So substitution. And alkyl halides can also undergo reactions that are called elimination reactions. So if you think about elimination, if you want to eliminate something, it means you're removing something, right? Something is going to be gone. And you can see that when you do this elimination reaction that's shown right here, what are you eliminating? Well, you're eliminating the halogen, right? It's lost as a halide. It might not be as abundantly clear, but you have a double bond here. And so you're actually also losing a hydrogen, right? One of the hydrogens from this molecule is being lost, and that's over here attached to the base now. Okay, so elimination, we end up losing atoms, and in a substitution reaction, we simply substitute the halide for a nucleophile. So substitution and elimination, and these are going to come up many, many times in this chapter. All right, well, what about a reagent like hydroxide, right? Sodium hydroxide. You know that sodium hydroxide is an ionic compound. It consists of sodium, which is a metal, and hydroxide, which is a polyatomic ion made up of nonmetals. Well, sodium hydroxide, I learned in general chemistry too, and I've seen it in this class as well. Sodium hydroxide is a base. So hydroxide can act as a base. But hydroxide also has a negative charge, which renders it a nucleophile as well. So in this case, we have this alkyl halide right here, and if we're reacting it with hydroxide, well, hydroxide can act as a nucleophile or a base. And so we get competing reactions. We can have a substitution product where we substitute the chlorine, in this case, for the hydroxyl from the hydroxide, or we can do an elimination reaction. Something I neglected to say on the last slide is that in the elimination reaction, the reactant is not a nucleophile, it's a base. So since hydroxide can behave as either a nucleophile or a base, we're going to get competing pathways here. Now you might be wondering, well, which one of these is the major product? Which one's more important? And that's going to be largely the focus of this chapter. In fact, we'll probably look at that a lot in our next class. All right. Also, a word that you're going to hear me say a lot in this class is substrate. And substrate is just referring to the alkyl halide. So this is our substrate. And if you're thinking, isn't that just the reactant or the reagent, or sorry, the reactant or the starting material? Absolutely. But again, in this chapter, we call it a substrate a lot. In fact, if you do this reaction, and this is going beyond what we've seen already, but the elimination product is actually the major product in this case, and the substitution product is actually the minor product in this case. And we're going to look at the reasons why that is. Okay, there's always going to be some kind of rationale to it, right? Organic chemistry is a logical subject. All right, well, let's talk about why an alkyl halide undergoes a substitution or an elimination reaction. Well, if we think about an alkyl halide, and I'll just draw something simple here. Let's say we have methyl bromide. I'll go back to that methyl bromide again. So we have a hydrogen here, we have a hydrogen in the back, we have a hydrogen coming out here, right? The carbon is just a good old sp3 hybridized carbon, 3 bonds to hydrogen, and a bond to the bromine like that. Well, we know the bromine is more electronegative than the carbon, and so it's going to pull electron density towards itself because it's more electronegative. Therefore, we have a polar bond, and the conclusion is that the carbon is going to be electrophilic. Right? It's going to have a partial positive charge, and so it's going to render it susceptible to nucleophilic attack, and that's why the nucleophile is attracted to that carbon, because it is electrophilic, opposites attract. There we go. And the halogen acts as a leaving group, and we touched on the idea of leaving groups in chapter 6 when we studied laws of leaving groups. So the halogen acts as a leaving group in this case, and for a substrate to undergo a substitution or elimination reaction, it has to possess a good leaving group. And so you might be wondering, what makes a good leaving group? Well, we're going to figure that out. I mentioned it in chapter 6 briefly to you, but here we have it in a lot more detail. And good leaving groups are nothing more than the conjugate bases of strong acids. So put another way, good leaving groups are going to be weak. They're going to be weak bases. Okay? Now, again, you can think about it either way. The way that I like to think about it is I think, okay, is this the conjugate base of a strong acid? It's going to be a good leaving group. If you like to think, well, this is going to be a weak base, that works too. Either way, you're saying the exact same thing. So if we look at strong acids, and strong acids would be these ones here, all the way up to hydronium. So we'll say the cutoff is right around here. These would be strong acids. So that means their conjugate bases are going to be weak, therefore they're going to be good leaving groups. But let's take a look at these acids. What are they? We have hydroiodic acid, hydrobromic acid, hydrochloric acid, nothing new there. We have hydronium. You've seen that a million times in general chemistry too. You've seen it a lot in this class as well. But there's a new one here that you've probably never seen before, and this is called para-toluene sulfonic acid. Organic chemists love to use acronyms, so this is called PTSA, which stands for para-toluene sulfonic acid. So this is a sulfonic acid functional group over here. And if you're thinking, hey, that kind of reminds me of sulfuric acid, this part here, you wouldn't be incorrect in drawing that conclusion. But you see that the pKa of these strong acids are all below 0. And that's a good rule of thumb, right? Students love rules of thumb. Good leaving groups are going to be the conjugate bases of acids that have a pKa below 0. So any acid that has a pKa below 0, its conjugate base is going to be a good leaving group. So that means that everything that's in this green box here is going to be a good leaving group. The iodide, the bromide, the chloride, this would be called a para-toluene sulfonate. Okay, so this would be a sulfonate, and here we have water, right? Water is the conjugate base of hydronium, which is a strong acid, and therefore it's going to be a good leaving group. Now, if we go beyond that, when the pKa increases, these are going to be considered weak acids. All right, you remember this from general chemistry too, that HF, hydrofluoric acid, is not a strong acid. Okay, it's got a pKa of 3, and therefore the conjugate base of acids like hydrofluoric acid, water, alcohols, and amine, right? Those conjugate bases are going to be poor leaving groups, okay, bad leaving groups. They're also strong bases, right? Much stronger bases than any of these. So now that we've decided what a good leaving group is and what a poor leaving group is based off of our knowledge on acidity, let's talk a little bit more about alkyl halides, right? Because we need to know a lot about alkyl halides in order to move forward in this chapter. I'm going to just say the name of an alkyl halide from time to time, and you need to know what I'm talking about. So we're going to have to talk about nomenclature of alkyl halides. And I can promise you that if you worked hard at your nomenclature for alkanes, which we looked at earlier on, right? We even looked at bicyclic compounds or bicyclic alkanes and cycloalkanes, looked at all kinds of things. If you worked hard at those rules way back in section 4.2, you're going to be able to use those steps to help you name an alkyl halide. All right, so same as always, we're going to identify and name the parent chain. We're going to identify and name the substituents. That means you got to be on your toes with respect to substituents like a methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. But we're also going to see halogen substituents. So if you have a fluorine, we call that a fluoro. Notice that it's UO, right? It's not fluoro, it's fluoro. If we have a chlorine, that would be a chloro. If we have a bromine, that would be a bromo. And if we have an iodine, that would be an iodo. So those are going to come up a lot, obviously, because we're talking about alkyl halides. Next, you assign a locant, which is nothing more than a number. It's just a TATC name that organic chemists use to mean a number for each of the substituents. And then we put everything together alphabetically. All right, there we go. The halide group, we're going to name that and locate that. So if we look at some examples here, a great way to study nomenclature is to always start out with a couple of examples. If you have a chiral center, right, we covered stereochemistry in chapter 5, so that can rear its head. And in fact, it will. Stereochemistry is going to be very important in this chapter, and we're going to touch on that today. Again, if you have a chiral center, you have to denote that in the name. So let's take a look at some examples here. The longest carbon chain here has 3 carbons. So we have a propane and we have a chlorine on the second carbon. So that would be 2-chloropropane. Look, if you were to have 1, 2, 3 carbons like this and put the chlorine over here, that would be 1-chloropropane. Okay, so it gets you kind of into the rhythm of it already. If you look at the longest chain here with this compound, we have 1, 2, 3, 4, 5 carbons in a row. That's our longest carbon chain. Even if you had started up here, 1, 2, 3, 4, 5, you're still going to end up with the exact same name, which would be 2-bromo-2-methyl-pentane, right? Remember, we have to include a locant for each substituent, and we list those substituents in alphabetical order, right? Bromo is going to come before methyl. The next one, I'm not going to go over the stereochemistry a lot in this chapter. You got to be pretty quick with your stereochemistry, right? You have a hydrogen in the back here, so you're going to go from 1 to 2 to 3, which is going clockwise. So this is an R configuration at our stereo center. So we have R. Again, we find our longest carbon chain, 1, 2, 3, 4, 5, 6, 7. So this is some kind of heptane. And we number the chain such that we give the first substituent the lowest possible number. Right, it's got nothing to do with adding up the numbers or anything like that. We just give the first substituent the lowest possible number. So we have 3 methyls and we have a bromo, but B comes before M in the alphabet. So we end up with this R5-bromo-2,3,3 trimethyl heptane, right? These are the kind of things that you'll be expected to name. Now, if you have a little alkane, a tiny little alkane, what would you do in that case? Simple haloalkanes, I should say, or simple alkyl halides are recognized by common names. And if you were to work in an organic chemistry or a lab doing organic chemistry or research or medicinal chemistry, common names are exactly what they're called. They're very common, okay? It's rare for a seasoned chemist to step outside of common nomenclature. And the reason why is it's just an effective tool for naming alkyl halides. Anyhow, if you're wondering what the heck do you mean by a common name? Well, the systematic name, which is what we talked about on the last slide, right? We had our halogen first and then we had the alkane after. Let me prove it to you. Look at all 3 of these, list the halogen somewhere near the beginning, and then we have the alkane at the end. Well, with common nomenclature, it's a little bit different. So with common names, what you do is you name the alkyl group first, and then you put the halide at the end, whether it's a chloride, iodide, bromide, or fluoride, okay? So let's say you had this molecule right here. Now, if you're wondering what the heck is this molecule, right? This molecule right here is just CH2Cl2, right? It's just drawn out in a bond line structure. Well, there's 2 ways that we could name that. If we name it using the systematic or the IUPAC nomenclature, we would call it dichloromethane. But if we name it using a common name, since I told you several times that a CH2 in organic chemistry is called a methylene group, right? If you have this CH2, this is called a methylene. I told you that if you have a CH, okay, this is called a methine. Anyhow, so we would call this methylene, and then we list the halide, which would be methylene chloride. And so dichloromethane is actually a very common solvent to use in the organic chemistry lab, very common. And so sometimes we call it dichloromethane, sometimes we call it methylene chloride, depending on the day, I guess. Okay, if you want to impress your friends, you know, you just use whichever name you feel like at whatever time. Anyhow, it's asking us to give IUPAC names to these molecules. Of course, our book always has a bunch of good problems where you can practice this. And if you look at the Chapter 7 module, I have a selection of problems from Chapter 7 that I recommend that you take a look at. Now, I'm going to go over the nomenclature of this first one kind of quickly. You got a couple options for determining the stereochemistry. You can either rotate this carbon-carbon bond so that you put the lowest priority group, which would be the methyl, so that you put that in the back position. But I think there's an easier way to do that, and this is my personal preference. Since the methyl group is pointing down here, you can imagine yourself, if you were looking at this molecule from the top, this is an eyeball staring down, right? If you were staring down from the top on this molecule, then the methyl group would be in the back, right? So what would you see if your eyeball was looking down, right? You'd see the iodine coming over here, you'd see the bromine over here, and you'd see the propyl group over there, right? And the methyl group would be pointing down. So if you follow the order of these groups, you go from the iodine to the bromine to the isopropyl group. You're going like this, which is counterclockwise. And so this is an S stereocenter. Okay, so that means the stereochemistry here at this stereocenter is S. All right, well, how do we name the rest of the molecule? What do? We find the longest carbon chain, which happens to be 1, 2, 3, 4, like this. We're going to number it starting on this methyl down here, 1, 2, 3, 4. The reason why is because then we have a 2, 2, and a 3. If we went this way, the other way, we'd have a 2 and a 3, 3, right? And 2, 2, 3 is going to beat a 2, 3, 3, right? Based on the first point of difference. So my numbering is correct. Now I've got a 2 bromo, a 2 iodo, and a 2 methyl. Well, bromine comes first because B comes first in the alphabet. Then we have I after B, and then we have M last. And so this molecule is going to be S2 bromo, 2 iodo, 3 methyl, and since I have 4 carbons in my parent chain, butane. So that's going to be the name of that molecule right there. All right. Now the next one, just in the interest of time, we'll just take a look at it for a second here. We're not going to go through it in dirty detail. So let me move this out of the way. That's for this one here. But for this one, I'm going to find my longest carbon chain, which happens to be 1, 2, 3, 4, 5, 6 carbons, like this. Okay, so that's my longest carbon chain. I'm going to number it in such a way that I give the first substituent the lowest possible number. Well, you notice that it doesn't matter which way you go. If you go like this, 1, 2, 3, 4, 5, 6, you have a substituent at 2, 3, 4, and 5. If you go the other way, 1, 2, 3, 4, 5, 6, you still have substituents at 2, 3, 4, and 5. So if you're wondering, well, which one is going to be correct? There can only ever be one correct answer, okay, in nomenclature. The rules are set so that we get an unequivocally a single name. You know, there's only one name, one correct IUPAC name for the compound. So the answer is this. If you have a tie like this, well, this group is a chloro. Okay, so we have a chloro here, and here we have a methyl. And since C comes before M in the alphabet, the numbering that I have in red is what you would go with. Okay, so in this case, you have to go by alphabetical order. So this means you have a 2, 3 dichloro, a 4 isopropyl, and a 5 methyl. Now I'm going to let you figure this out on your own time, but the stereochemistry at both of these chiral centers is R. Now, how do you denote that you have the two different chiral centers? You would say 2R, 3R at the beginning. You put that in brackets, and then you're going to list your substituents in alphabetical order. So we have 2,3-dichloro, 4-isopropyl, 5, oops, I'm going to run a spacer, 5-methylhexane. And so the methylhexane should be connected. It should be all one word. But remember that we ignore all prefixes except iso, cyclo, and neo. And so C comes before I in the alphabet, and then M comes after those. Okay? So there you go. So those are some IUPAC names. A little bit of practice on stereochemistry. So you can imagine that stereochemistry is going to come up repeatedly in this class. Okay? Stereochemistry comes up a lot in Organic Chemistry 1 from now on, and it's going to come up a lot in Organic Chemistry 2 as well. Something else that you're going to hear me refer to in this chapter are Greek letters. You need to know a little bit of the Greek alphabet. I mean, not a whole lot. All you need to know really is the first 4 letters. We have alpha, beta, gamma, and delta. So these are the lowercase first 4 Greek letters from the Greek alphabet. So if you're a member of a fraternity or sorority, maybe they made you memorize the entire Greek alphabet. I don't know. But anyhow, Greek letters are used a lot in organic chemistry to label carbons of an alkyl group that's attached to an alkyl or attached to a halogen. And the reason why it's so important is because substitutions occur at the alpha carbon. So the carbon that the halide is attached directly to, we call that the alpha carbon. And then going out from there, you'd have beta, gamma. If you had another one here, for example, if you kept going, this would also be a gamma carbon. If you went again, this would be a delta carbon, so on and so forth. Anyhow, we don't generally look past beta carbons a whole heck of a lot in this chapter, but you need to know that a substitution occurs at the carbon that is attached to the halide, and we call that the alpha carbon. All right, now what about the substitution on that alpha carbon? That's going to be important to us as well. So when I describe an alkyl halide as being primary, secondary, or tertiary, you have to know what that means. For example, if you have an alkyl halide that has only one R group attached to the alpha carbon, that's a primary alkyl halide. If you have 2 R groups attached to the alpha carbon, it's a secondary alkyl halide. And if you have 3 attached to the alpha carbon, right, these are all alpha carbons that I drew in here, 3 substituents on your alpha carbon, it's tertiary. Students don't usually struggle with this, okay? But I would say that having a knowledge of what a primary, secondary, and tertiary alkyl halide is going to be really, really important moving forward. And the reason why is because we're going to look at scenarios where a primary alkyl halide is going to react differently than a tertiary alkyl halide. If you're very astute, you might have even noticed that on my first couple slides when I talked about substitution and elimination. You don't have to go back and look at it, but if you did, you'd probably notice that on one of the first few slides that the substitution reaction occurred at a primary alkyl halide and that the elimination occurred at a tertiary alkyl halide. Anyhow, our book goes into some detail about the uses of alkyl halides. He actually goes into so much information about alkyl halides, and it makes me wonder if David Klein didn't work with alkyl halides at some point in his life, because he seems like he's really interested in them. Here's an example of a very famous alkyl halide, which is DDT. I'm sure a lot of you have heard about DDT and how it's used. It was used as an insecticide for many, many years until it was determined to be toxic to animals, and I think it might be slightly carcinogenic or something like that. But it did save a lot of lives by eliminating a lot of deaths attributed to malaria in the third world. Anyhow, there's a whole book written about DDT. Does anybody know what book I'm talking about? The book written about DDT? It's not going to be on your quiz. No? Okay, well, there's a very famous book written about DDT. I won't tell you the name of it. You can Google that yourself. Anyhow, we also have lindane, which is an alkyl halide. So if you're wondering, where would I find an alkyl halide in real life? Well, lindane is actually used in lice shampoos. So if you've ever had head lice and had to use a shampoo treatment for lice, you might have used lindane. I'm going to skip this next slide and we'll come back to it in a second. But some other organohalides, chemists thought for a long time that organohalides were all poisonous because of compounds like PCB. So PCB is a polychlorinated biphenyl, so PCB. And I'm sure a lot of you have heard of PCBs. They were used as coolants and insulators, but they were determined to be bad for the environment. I think they're carcinogenic. A funny thing about PCBs is my dad worked for his father, my grandfather, for a number of years in construction, and they used to build foundations, and they would build these forms to pour the concrete inside of. And my dad told me when he was a teenager that his father showed up one day with a whole bunch of oil that they were going to use to lubricate these forms, these wooden forms. And he said, where did you get this oil from? And he said, oh, it came from Transformers. And he said they had their shirts off and were just rolling the stuff on and brushing it on. So working with this carcinogen. And I have a note here in my slides that I'm looking at that one of my students asked me, is that the same thing as PCP? Okay, so PCP is angel dust if you have ever studied illegal drugs. So PCP is phenylcyclidine, so that's something that's a little bit different. That's used for its mind-altering effects. Anyhow, other things that are other organohalides, Splenda, which is sucralose. So sucralose, and you can look at the structure of Splenda. I'm sure a lot of you have heard of Prozac. So Prozac is an antidepressant, and it has fluorine in it. Antimicrobials like Bronopol. Anyhow, the book goes into quite a little bit of detail about this. So kind of interesting stuff. It's always fun to learn. What are these kind of compounds used for? All right. Well, let's step back here and try some more nomenclature problems. So it says assign a systematic name for each of the following compounds, right? If I was to ask you to name this compound based off of what we learned in chapter 4, you would just call that methyl cyclohexane. But now we have an alkyl halide, right? We've got a bromine here. And since we have two substituents on our cyclohexane, we're going to have to give those a locant. Since they're both on the same carbon, we would call this 1 bromo, 1 methyl, right? Bromo is going to come first because B comes before M in the alphabet. So we have 1 bromo, 1 methyl cyclohexane. All right. Could anybody tell me what the stereochemical configuration of this chiral center is? I'll see if anybody can do it quickly. Hold on. All right, Skylar says it's R. I think you're right. I think you're right that it's R, right? This will be the highest priority group. The butyl will be second, the propyl will be third, and the ethyl is in the back. So we go from 1 to 2 to 3, which is clockwise. And so, yes, the relative or the stereochemical configuration of that chiral center is R. We find the longest carbon chain, which I think is kind of abundantly clear in this one. And we would start numbering from the right-hand side, 1, 2, 3, 4, 5, 6, 7, 8. So this is some kind of octane. We have a 4-chloro, a 4-ethyl. So we put all that together in one big, beautiful nomenclature sandwich, and we get our 4-chloro, 4-ethyl octane. Something else that's kind of a nuance in terms of nomenclature is that the stereochemical configuration in nomenclature is always put in a bracket like this. And if you look at it in the textbook, the stereochemical designation, RRS, will always be italicized. Let's do the last one. Again, if we find the longest carbon chain, again, I think it's kind of clear in this one that it's these 6 carbons here. Well, we're going to start numbering from the right-hand side. 1, 2, 3, 4, 5, 6. Why? Because we have 2, 2 here. If we were to number starting from the left, we'd only have a 2. So we have a 2,2-dimethyl and a 5-fluoro. So if we put all that together, we've got 5-fluoro, 2,2-dimethyl hexane. Could anybody tell me what the stereochemical configuration of the chiral center is? Is this R or S? Would that be R or S? Brandon says it's R. Yeah, I think you're right, Brandon, because you go from the fluorine, which is priority number 1. All of this is going to be number 2. So we could just label that as number 2 down here. This will be number 3, the methyl. So we're going from 1 to 2 to 3, which is clockwise. The hydrogen is in the back. And so this compound is an R compound. So again, we put that in brackets. with a hyphen like that. There we go. Good. All right. So you'll see that as you progress in organic chemistry, you'll get very good at assigning stereochemical configurations, and you'll kind of develop some mind tricks and stuff of your own, so you won't have to spend as much time as you did in chapter 5. Well, that covers the first two sections of chapter 7, a big chapter. Let's move on to section 7.3, which is kind of where the rubber meets the road, where we really start looking at some curved arrows, right? We looked at curved arrows when we studied resonance earlier on in this class, and then we looked at curved arrows even more in the last chapter when we studied a loss of leaving group, a rearrangement, a proton transfer, nucleophilic attack. But we're going to see those curved arrows come up again and again in the remainder of this chapter. So let's talk about that substitution reaction. Let's go look at that substitution reaction. A substitution, if you're going to substitute the halogen or the halide for a nucleophile, that means that the halide has to act as a leaving group. So the leaving group has to leave, is what I'm trying to say. Okay, so we've got to have a loss of a leaving group and a nucleophilic attack. We're going to have both of those, LLG and an Na. Well, there's two different ways that could happen. Right? It might not be abundantly clear right now, but let me show you. The two possible ways, first one is what's called a concerted mechanism. Okay, concerted means nothing more than at the same time. Okay? It sounds like a big fancy word, but it means nothing more than just both things happen at the exact same time. So that means the nucleophilic attack and the loss of leaving group are going to occur simultaneously. Look what happens. We have our curved arrow, our nucleophile is attacking the alpha carbon, right? Notice that this carbon here is that's the alpha carbon. Okay, it's the carbon attached directly to our halogen. And then the leaving group is leaving simultaneously, right? Two arrows at once. If you were to draw these one at a time, it would be incorrect. It would not be a concerted mechanism. It would not represent the two processes occurring at the same time. Now, we can have a situation where they occur one at a time, okay, which we call a stepwise, which is just a fancier way of saying one at a time. A stepwise mechanism shows the loss of leaving group occurring first, and then you end up with a carbocation, right? If the leaving group just leaves as a halide, well, you're going to be left over with a positive charge. So you're left over with a carbocation. This is one dandy electrophile, isn't it, my friends? Okay, this is a really good electrophile. And so the nucleophile is just going to attack that. But notice the difference, right? There's a big difference. And hopefully you're noticing that here they're showing a primary alkyl halide undergoing the concerted mechanism. And here they're showing a tertiary alkyl halide undergoing the stepwise mechanism. All right. Now this introduces us to the concept of SN2 and SN1 mechanisms. Now, instead of waiting until we get to the SN1 section of the book, I want to tell you something that a student told me or said to me in probably 1996 when I was studying organic chemistry for the first time. I was in a class just like where you are. We were talking about SN1 and SN2 reactions in the lab. Me and this girl who was in my class, and she said something I never forgot, and that is the concerted mechanism is an SN2 mechanism. And the way she described it was SN2 is SN together. Okay, that's what the 2 stands for. It's not what the 2 stands for, but that's the way she described it. And when we have a stepwise mechanism, she called this an SN1, and SN1, she called it one at a time. Okay, it's the only person I've ever heard say that. Maybe she invented it herself. Maybe she did. Maybe she stole it from somebody else. I don't know. But it's something I never forgot. So an SN2 reaction is going to be SN together. Both steps are happening together. And an SN1 is SN1 at a time. It's a stepwise mechanism. Well, let's get into that SN2 even more, because that's the title of this section is SN2. So that's going to be the focus of section 7.3. Nucleophilic attack, loss of leaving group occurs at the same time. Now, if you're wondering what the hell is SN2, what does that stand for? Well, the reason we call the concerted mechanism an SN2 mechanism is that the letter S simply stands for substitution. The N stands for nothing more than nucleophilic, but here's a little bit of general chemistry too, rearing its head again, right? It's a bimolecular reaction. You remember that when you determined reaction orders, right? A first order reaction, a second order reaction, a third order reaction. If we study the kinetics, and again, this is going back to General Chemistry 2, what we find is that the rate of this reaction shown right here, this concerted mechanism, is equal to the rate constant multiplied by the concentration of the substrate and the concentration of the nucleophile. So if both of these are to the power of 1, which we don't show, then the overall order is 1 plus 1, which is 2, and therefore it is bimolecular. Again, what does it mean if both the substrate and the nucleophile's concentrations show up in our rate law? It means that the rate of this reaction is going to depend on the concentration of both of these, doesn't it? Right? It's going to depend on both of these. If you really want to take it one step further, since rate, and this is just kind of a review of General Chemistry 2 for all my students who want to write the MCAT exam or maybe a DAT exam or something like that, right? Rate is in moles per liter per second. If the concentration of both of these is in moles per liter, what would the units of K be? Okay, you should be able to work that out if you don't have them memorized from General Chemistry 2. But in this case, the units of K would be equal to molar to the -1, seconds to the -1. You could try the math if you don't believe me, but that's what the units would be. Okay, anyhow, let's get back into it. Let's take a look at a question that involves an SN2 reaction. So we have 1-iodopropane or propyl iodide. And it says here, the following substitution reaction exhibits second-order kinetics. So that tells us that it's an SN2 reaction. And here it is. So we have propyl iodide. We're reacting with the sodium hydroxide. We make this molecule called 1-propanol, and then we end up with the salt sodium iodide. We could try drawing the mechanism for this. It doesn't ask us to do it, but hey, it's the land of the free. Let's give it a try. If we were to draw out the hydroxide like this, here's our alpha carbon. And so the curved arrow is going to go from the nucleophile to the alpha carbon. That's our nucleophilic attack. And then simultaneously, since this is an SN2 process, we're going to have the loss of leaving group, right? Both of them are occurring at the same time. Anyhow, question A says, what happens to the rate if the concentration of 1-iodopropane is tripled and the concentration of sodium hydroxide remains the same? Well, if this is an SN2 process, and this is a really easy question for me to ask on your quiz, is that you got to understand the rate law, right? That the rate of this reaction is going to be equal to the rate constant times the concentration of the 1-iodopropane times the concentration of our nucleophile. So if I double the concentration, or sorry, triple the concentration of the 1-iodopropane, and I don't change the concentration of the sodium hydroxide, can anybody tell me how much the rate will increase, or how it will change? Yeah, thanks, Skylar. It's going to be 3 times as much, right? If I'm initially starting out with a concentration of 1 for each of these, let's just say it's 1 for each of them, then we have K times 1, okay? The rate constant times 1. But if I triple one of them, then I'm going to have my rate is going to be equal to K times 3. So 3 times the concentration times 1. So that's going to be equal to K times 3. So it's going to increase by a factor of 3. So rate is tripled. Now, if you think the question is too easy, good. Okay, it's not meant to be a complicated question. Let's take a look at B. It says, what happens to the rate if the concentration of 1-iodopropane remains the same and the concentration of the NaOH doubles? Could anybody tell me what would happen to the rate then? What would happen if I doubled the concentration of hydroxide but left the concentration of the electrophile or my substrate the same? Yeah, it's going to double, isn't it? Because the concentration of the 1-iodopropane doesn't change, but I double this. 1 times 2 gives me 2. So I'm going to have K times 2. So the rate is doubled. Nothing more than that. If we take a look at C, there used to be a question pretty much identical to this one on the ACS final. It says, what if you double the concentration of iodopropane and you triple the concentration of sodium hydroxide? So you'd have 2 times the concentration of iodopropane and 3 times the concentration of sodium hydroxide. That would be K times 2 times 3, which is 6. And therefore, the rate, we'll say rate is 6 times faster. Okay. Rate is jacked up big time. All right, there we go. So it's a good feeling, you know. It's one of the best things about organic chemistry is understanding things like this, understanding rate laws, and then feeling like you can control nature. You know, just do what I want with this reaction. I'll control the concentrations and control the rate, right? I'll set this reaction up so it'll be done by the time I'm done smoking a cigarette in the parking lot. Okay, let's see here. Stereochemistry. Hey, if you liked the stereochemistry chapter, you're going to love the rest of this class. If you didn't like it, it would be a good opportunity for you to maybe take a step back over the weekend or tonight or something and just spend some more time practicing using the Kahn-Ingold pre-log rules. Well, if we take a look at this SN2 reaction that's occurring here, okay, we have a secondary alkyl halide right here. So this is a secondary alkyl halide, and you could name it if you want. This is S2-bromo-butane. Anyhow, here's the alpha carbon right here. The nucleophile has to attack that alpha carbon. But what's interesting is that the nucleophilic attack doesn't occur like this. If I draw in my lone pairs on my hydrosulfide, so that's the name of this polyatomic ion, it's a hydrosulfide, the nucleophilic attack doesn't occur like this. Okay, now before I told you, oh, you can just draw your arrows any old which way. Okay, well, the nucleophilic attack doesn't actually occur on that side or that face of the molecule. The nucleophilic attack actually occurs from the back like this. And when it attacks from the back, what it does is it causes these groups to, those groups to invert or flip. And if you read the textbook, you would have seen that it flips like an umbrella in the wind, okay? And what that does is it inverts or switches the stereochemical configuration at the chiral center. So you see how all of these groups are on this face of the molecule here. Well, after the nucleophilic attack occurs and the loss of the leaving group occurs simultaneously, we end up with the thiol on this side, and you see that these groups are now on the other face of the molecule. And if you don't believe me, you can just evaluate the relative stereochemistry and see that it inverted. It went from S to R. And so we say that this reaction is stereospecific. You start with one stereochemical configuration, S, and you end up with the opposite. If we were to start with R, we'd end up with S. They are opposites. Now, normally, I've taught this class remotely, a couple times so far. I've explained this concept, I should say, remotely a couple times. Now, normally, I stop my lecture right here. What the heck is going on? What am I doing? Jeepers. The iPad is a great tool, but it can be pretty frustrating sometimes. There we go. So if I stop like this, there's no good way for me to really demonstrate this to you with a model. But if I just show you like this, and this sometimes works, okay, I'm not double jointed. I can't invert my hand. But if you have the leaving group over here, right, and the nucleophile comes in and attacks, what it does when it does that is it causes these groups to invert. So they end up on the other side like that. Now that's the best I can do, right? You have them like this, nucleophile comes in, and then they're like, get out of the way, everybody, right? And then it inverts. So that's what it means, like an umbrella flipping in a wind. It doesn't mean it's flipping like a pancake or anything like that, but that's what it means, the flipping or the inversion of the stereocenter. Give me a thumbs up if you follow me on the concept. Not the easiest thing for me to explain because I don't have a model kit that you can bend the bonds or anything like that, but it's just the idea of the flipping of the stereocenter. Okay, because the reason I want you to understand what that means by the umbrella flipping like in the wind, and the reason I'm harping on this for so damn long, is because I have a lot of students who just want to memorize it. Okay, if it's S, it's going to be R. Well, later on, we're going to look at cases where it's not stereo-specific; it's what's called stereo-selective, and so yeah, just having an idea of what that umbrella flip means is a good thing. Okay, thanks, Courtney. I'm glad that you find that even a little bit useful. Well, there's a twofold reason why the nucleophile in this case attacks from the back. And I'm not joking. I had a student who kept laughing about this when I taught this to the majors. But this is called backside attack. So backside attack. Every time I'd say it, she'd start giggling. But anyhow, the backside attack is what it's actually called. And the reason that it attacks from the back is there's twofold, okay? Two reasons. Reason number one and reason number two. Reason number one, I expect you to know what that is, okay? And it's basically, it says the electron density repels the attacking nucleophile from the front side. So look, all it means is this. Since the bromine is delta negative, right, and it's got lone pairs all around it, that is going to cause a repulsion between the negative here and the partial negative here. So that is reason number one, reason number uno, why this doesn't happen, okay? That's reason number one why we get backside attack. The second reason deals with molecular orbital theory. I'm never going to ask you about this, okay? Our book goes into a little bit of detail about it, and he draws this MO diagram here. The idea is, and I used to go over this with my students, but it's not covered in the ACS, so I'm not going to ask about highest occupied molecular orbital and lowest unoccupied molecular orbital, but I'll just leave it at, if you want to read about that, and it's just a very quick blurb, it's maybe like 3 sentences in our book, you can do that, but I'm not going to ask you about it. Again, just understanding that it's going to resist that partial negative charge on the bromine is good enough for me. So here we have the backside attack occurring right here. And then we have our product, right? We've seen this already 2 slides ago. But the substrate is going to pass through a transition state, okay? A transition state. Remember when we looked at reaction coordinate diagrams and we said the peaks for transition states, it was akin to taking a picture of a person when they're hovering in the air if they were trying to stand on top of a desk. Well, the transition state that's going to occur, okay, would look something like this. We're going to have the alpha carbon. It's going to have the methyl group attached to it. It's going to have the hydrogen in the back like this, but the ethyl group is going to be coming straight down like this. And remember, it's a transition. It's not going to be the substrate, and it's also not going to be the product. It's going to be kind of in between. And the way that we represent this is with a dashed bond to the sulfur that's incoming, right, which is going to be delta negative. And then we have a dashed bond to our bromide, which is going to be leaving, which is also delta negative. The transition state is always put inside square brackets like this, and we always use this double dagger, which is the transition state symbol, right? We call it the double dagger. That would be a good name for a bar for organic chemistry. We call it the double dagger. Anyhow, so here we have the double dagger, which represents the transition state, and here we have a transition state here. Now, transition states are something that I don't ask my students to draw, even when we did paper quizzes pre-pandemic and post-pandemic. I'm probably not going to ask you to draw transition states either, but you can guess what I'm going to say next, is that it's important that you understand what the heck it is, okay? You see that this bond is being formed, okay? Maybe we could even put that in here. So this is the bond being formed, and it's not completely formed, is it? And this is the bond being broken, and it's not completely broken, is it? Right? So this would represent, again, a maximum on our reaction coordinate diagram. Let's try a practice problem. Here would be a great practice problem for somebody studying chapter 7. This would be a really good kind of beginner problem. It says, draw the product for each of the following SN2 reactions. Well, I only got one on here anyway. So we have S2-chloropentane reacting with sodium hydrosulfide. Well, 2-chloropentane or S2-chloropentane is going to be our electrophile, right? This is going to be our electrophile, and this is going to be our nucleophile. So this means that you've got to be able to draw S2-chloropentane, right? It's not just going to be given to you. The ACS or the MCAT, they love questions like this because you got to do 2 things. Not only do you have to understand SN2, but you got to do a little bit of nomenclature. So what I do when I'm drawing these, or not now, I've been studying organic chemistry for a long time, but if you're just learning, you know, like where you guys are, here's what I recommend. I would draw the parent chain, so 5 carbons like this. On the second carbon, right, that would be carbon number 2. I start by drawing a dash, okay, like this, and draw the chlorine, and then just evaluate it and say, is this R or S? Oh. And the reason why I draw as a dash is because if this was R and I wanted it to be S, all I'd have to do is shade it in, right? So I always start by drawing a dash. If you don't like that technique, don't use it, but it's just kind of a trick that I use. But look, if we go from 1 to 2 to 3, so that's going clockwise, which is R. The proton is coming out towards us, so we would reverse it. And so this is actually S2-chloropentane. So that's the correct electrophile. Now we're going to react it with the hydrosulfide. Sodium is a spectator ion, right? If you want to include the sodium, you can, but it's not required at all, okay? And I'll explain why after, but let's just start by drawing out the hydrosulfide. Okay, so this is called hydrosulfide, right? If you have this is hydroxide, so hydrosulfide in here. There we go. So let's get some practice in drawing some curved arrows. We have our nucleophilic attack, and we have our loss of leaving group. Maybe I should even draw the lone pairs on my chlorine like that. And then I'm going to end up with my product. But since this is an SN2 reaction, it is going to occur with inversion of configuration. If you're like, what the hell is conversion of configuration? It was this right here, okay? This change in configuration is called inversion of configuration, right? It's inverting from S to R in this case. And so all we have to do to represent inversion of configuration is just flip the stereochemistry on that bond. So this, since this bond to the chlorine is a dash, the bond to the sulfur is going to be a wedge. So we just draw our longest carbon chain. So 1, 2, 3, 4, 5, like that. And we draw this, and there we go. That's it. And then we'd also have the chloride. Okay. And there we go. And that proceeded with inversion of configuration. This is the umbrella flipping in the wind, right? This stereocenter here is S. Here we go from 1 to 2 to 3, going like this. That's clockwise. And so this stereocenter is R, right? We flip from S to R, like that. Now, again, if you're the kind of person who is wondering where the hell is the sodium during all this, it's just out, doing its own thing. Well, look, if we were to draw the sodium, which is just a spectator ion, here we have the sodium hydrosulfide. Well, you end up with sodium chloride, right? But again, as I've told you several times, and this goes way back to the beginning of our class, organic chemists love to leave spectator ions out, right? They're just spectating. All right, give me a thumbs up if you follow me on that one. Backside attack, SN2. Inversion of configuration. If we start with S, we end up with R. Start with a dash, we end up with a wedge, and the opposite would also be true. Good. Great. Excellent. Well, let's move on from there and talk about the kinetics. Right? Gen Chem 2 keeps rearing its head in organic chemistry. Well, it says here that less sterically hindered, so that means less bulky electrophiles are going to react more readily under an SN2 condition, and tertiary alkyl halides are too hindered to react via the SN2 mechanism, right? What does the SN2 mechanism involve? It involves a nucleophilic attack and a loss of leaving group occurring together, SN together. So if I have a nucleophile, here's this beautiful, tasty nucleophile. If it wants to attack a methyl, well, all you have attached to the alpha carbon are those 3 little piddly hydrogens. This is the smallest atom in the universe. Therefore, there's going to be no steric hindrance. Look, if the nucleophile's incoming, okay, if that's your nucleophilic attack right there, well, now you've got a methyl group in the way. That's going to slow it down somewhat. If you had 2 methyl groups, wow, now you got this guy and then this guy here. And then if you try to do it with a tertiary, it's not even going to work. And the reason why is because now you've got 3 methyl groups, okay? It's just about the amount of substitution that is on the alpha carbon. So much so that you find that really only methyl and primary are going to give you really good reactivity towards SN2 reactions. Don't believe me? Take a look at this table right here. If you're the kind of person who likes to have everything in graphs and numbers, well, this will help you out a lot. Just looking at alpha substituents, just ignore this part of the table for now. We're just looking at this side over here. If you have an alkyl bromide and you treat it with iodide and acetone, so acetone is just nail polish remover, makes a dandy solvent for SN2 reactions, you end up with an alkyl iodide and bromide. Okay, good. So that's just an SN2 reaction. Look, if you're the kind of person that needs to put a curved arrow on everything, there's your nucleophilic attack, there's your loss of leaving group. Hot dog, we have a wiener. Okay, well, if I have only the 3 hydrogens on here, you can see that it's going to occur 145 times faster than if I have a methyl group. Look what happens when I have 2 methyl groups. Whoa, whoa, whoa. Nelly, you can see the reactivity drops off a lot. If you take 145 divided by 0.008, okay, this reaction is 18,000 times faster than this one. So, wow, you're thinking, that's going to take too long. I don't have that kind of time. And then if you have 3 methyl groups, right, if you have a tertiary, so we're going from a methyl to a primary to a secondary to a tertiary. A tertiary is so crappy, it's not even going to work. Okay? Now, here's something that is not as intuitive, but let me show it to you. What if you have a substituent at the beta? Okay? Something we haven't really addressed yet. So here at the beta, we have just the 3 hydrogens. So 1, 2, 3 hydrogens, right? That's just ethyl bromide. Well, if we assign that a relative rate of 1, you see what happens when we start adding methyl groups to that beta carbon? Look what happens when we go from a methyl to 2 methyls to 3, is that the reactivity drops off a lot. And what's interesting about this is this guy right here. If you think about this, you have 3 methyl groups at the beta carbon. This is so crappy, totally useless. Useless reaction, okay? It's just too damn slow for it to be a good reaction for an organic chemist who has a life expectancy of, I don't know, what's the life expectancy of in America? I don't know, 72 or something like that, 73, okay? We only get a finite lifetime, and so it's too slow to be useful to us. But what's interesting about this, and this is one of the neatest points that he makes in this chapter, because as your teacher, I want you to get a good grade in this class. I want you to maximize your potential in organic chemistry. Believe me, if you do well, it's a good thing for me too. And this is a perfect example, what I have in this red box, of why you can't memorize your way through everything in organic chemistry. Because if you go on YouTube and you just search SN2 and start watching videos, you know what they're going to tell you? And they're right. They're going to say a primary alkyl halide is super reactive. Well, hold the phone. This is a primary alkyl halide, right? That's a primary alkyl halide, but it's super unreactive. And it's because of all those substituents on the beta carbon. So what he says in the book is, he says, this is the perfect example that shows how you can't memorize your way through everything in OChem. And sometimes it's just going to have to be applying your understanding. Okay, it's what I love about the subject the most. Okay, as one of my former employers told me, he said, Dion, you got a great memory. It's just very short. Anyhow, so let's take a look at the kinetics again. If we look at a reaction coordinate diagram, here's a nucleophilic attack and loss of leaving group occurring simultaneously, right? This is just a plain old SN2 reaction. We have the nucleophilic attack and the loss of leaving group, but here's our transition state, which is the maximum, okay? This nucleophile, CN minus, you should know what that is. It's cyanide. Yes, the same cyanide they drank in Jonestown. Anyhow, so if we have cyanide acting as a nucleophile and bromide acting as a leaving group, the relative energy, or the activation energy that leads us to the transition state, is going to determine the rate of reaction. Again, this is going back to your general chemistry days, right? You learned this in general chemistry too, that the higher the activation energy, the slower the reaction. The lower the activation energy, the faster the reaction. That's why catalyzed reactions are so fast, right? Because you lower the activation energy. Again, if you're the kind of person who needs a picture, if you have a methyl, you can see you have a certain activation energy associated with that. Once you go to a primary alkyl halide, what's going to happen? The activation energy is going to increase. Once you go to a secondary, it's going to increase even more. And tertiary isn't even on here. Why? Because it's so slow, it's immeasurable. Okay? Or it's probably measurable to some extent, but it's crappy. Okay? It's useless. Right? As organic chemists, we're looking for useful reactions. What's going to generate a new cancer, a cancer-fighting drug? Well, if you have a bunch of useless reactions, you're not going to be any closer to that. What I was saying a couple of minutes ago when I was going on this big diatribe about this molecule, that is a primary alkyl halide, but it has the 3 substituents at the beta carbon. Therefore, it's primary, but it's unreactive in an SN2. this is the picture that he uses to show you, you know, this is why it's unreactive. It's because this is just the alpha carbon is just way too sterically hindered with this T-butyl hanging off here. Okay. Again, he goes into a little bit of, a little bit of a, what's the words I'm looking for here? I don't know, a little bit of a soapbox speech where he, explains understanding versus memorizing. Anyhow, here you go. So neopentyl bromide. You know, the neopentyl group is something that I'm sure some of you have seen it on your travels. You know, maybe when you were studying methyl, ethyl, propyl, isopropyl, butyl, terbutyl, all that stuff. You might have seen the neopentyl group show up. I think I might have even mentioned it once in class. Anyhow, it doesn't come up a lot in this class. All right, so that finishes the first three sections. Now we're on to section 7.4, where we talk about nucleophilicity. You're probably standing back and just going, man, we're really analyzing the heck out of everything. Electrophiles. We looked at all these different alkyl halides. Why are some good electrophiles? Why are some poor? We looked at alpha carbons, beta carbons. Now we're switching to nucleophiles just to show you how much detail we have to go into. We're not only going to talk about nucleophiles, we're also going to talk about the solvent that you do the reaction in. Okay, what are you doing there? What's your solvent? We're going to talk about that next. Anyhow, consider the factors. That's not one word. Consider the factors that contribute to the strength of a nucleophile. We talked about this in chapter 6 rather. Charge. So a negatively charged nucleophile or a negatively charged atom is going to be a better nucleophile than a neutral one, right? If you have hydroxide, so here's hydroxide, and you compare it to water, well, hydroxide is going to be the oxygen is going to be a better nucleophile than the oxygen in water, right? It's got a negative charge on it. Okay, and a nucleophile is a nucleus lover, something with a negative charge, a full negatively charged anion is going to be a better nucleophile than something that's just got a partial negative charge on it, right? So we need to have a good nucleophile for an SN2 reaction. Another factor that contributes to nucleophilicity is polarizability, which is nothing more than the ability of an electron cloud to distort so that it can attack an alpha carbon. And polarizability is related to the size of an atom. So the bigger the atom, the further the electrons, the valence electrons are from the nucleus, and the greater ability they have to polarize themselves, and therefore bigger atoms are going to be stronger nucleophiles. For example, if you were to compare, and I think I might have gone over this in the last class, I can't remember. If you were to compare the nucleophilicity of H2O versus H2S, H2S is going to be a better nucleophile because sulfur is more polarizable. Anyhow, there we go. So commonly used nucleophiles that are going to come up all the time in this class are shown here in this table. David Klein, the author of this textbook, loves tables, and I love him for it. Does a really good job of making good, concise summaries for our students. Commonly used nucleophiles, let's go over them. We have iodide, bromide, chloride, right? Those are the halides. I told you that a fluoride is not going to show up as much in this class. A fluoride can be an amazing nucleophile depending on the situation, but our book doesn't use it very much. This one is a hydrosulfide. So a hydrosulfide, I wrote that down in the last, a couple slides ago. When you have RS minus, that's called a thiolate. This is called an alkoxide. This is called a hydroxide, and this is called cyanide. And then weak nucleophiles are things like water or an alcohol. So you need to know what strong nucleophiles are and what weak nucleophiles are. So you should have this table memorized to some degree. Now you notice that everything over here has a negative charge, and the weak nucleophiles are all neutral, so that's kind of easy to remember. I also told you the difference between polarizability. So the more polarizable an atom is, the better nucleophile it is. But now we're going to talk about how solvent affects nucleophilicity. Before we do that, I'll put memorize on this. I would suggest memorizing this table because it's going to come up so much. And if you're like, oh, no, not another thing to memorize. Well, there's some truth in that. But also remember that once you do the practice problems and you go over problem after problem after problem, you start to get the hang of it, right? It becomes less memorization and more just intuition once you've seen them over and over, all right? The key to memorization is just repetition, right? Now, what would be an appropriate solvent for an SN2 reaction? The answer is that we want to use what's called a polar aprotic solvent. Now, you can know what polar is because everybody should know what a dipole is in a molecule. Say, for example, acetone falls under the umbrella of polar aprotic solvent. So you can see it's got a dipole here. But what does the protic thing mean? Well, a protic solvent, okay, is one that can engage in hydrogen bonding. Now you notice that over here on the protic solvent side, okay, that each one of those solvents, whether it's water, methanol, ethanol, acetic acid, or ammonia, they all have a bond between hydrogen and either oxygen or nitrogen, right? So all of those solvents are capable of hydrogen bonding. So if you see a solvent that can hydrogen bond, we call that a protic solvent. All of these solvents are polar too, but a polar aprotic solvent, all of these solvents have dipoles in them, right? So we have acetone, which I'm sure you've heard of a little bit. It's nail polish remover. The next one is DMF. The first post I ever made on Twitter was about a book called, and I'm not kidding, the title of the book is DMF. One of my friends had it. I saw it. I just had to read it. It's a whole book just about this one solvent. Amazing book. The next one is HMPA. Hexamethylphosphoramide. A lot of organic chemists hate HMPA, not only because it's really dangerous, not in terms of its reactivity, it's not going to explode in your face or something like that, but it can be readily absorbed through the skin, and it also has to always be prepared fresh, so you always have to distill it, and distilling it is a big PITA. The next one is dimethyl sulfoxide, DMSO. DMSO has a pretty high boiling point. Another thing about dimethyl sulfoxide, it's not nearly as annoying as HMPA because dimethyl sulfoxide, you don't have to purify it when you want to use it, but it gets absorbed through your skin really quickly. I'm not kidding. Like, I mean, in seconds. And if you get a lot of it on your skin, and I'm not joking, it sounds funny, but if you've ever eaten canned corn that was cold, okay, so if you don't warm it up, well, and you're like, why would you be eating that, Mr. Dion? I don't know, okay, single for a long time, okay, anyhow, but if you've ever had canned corn and you know the taste of canned corn, that's the taste that will be in your mouth as soon as you get dimethyl sulfoxide in your skin. Sounds funny, but it's true. Okay, I spilled a whole bunch of it on myself one time. Anyhow, the next one is acetonitrile. Oops. Acetonitrile is a polar solvent, right? It's got a dipole going this way. There's also a slight dipole going this way. This isn't discussed in our book, but an sp hybridized carbon is going to be more electronegative than an sp3 hybridized carbon. Anyhow, so acetonitrile is a polar solvent. Something interesting about acetonitrile that I didn't know until I started working in industry is that it can give you a really bad headache. One time I was working with acetonitrile and I had it in my fume hood, but I left the top off of a big bottle of it. And the guy who worked next to me said, like, whoa, put the cover back on that. It gives you like a nasty headache. And he said, I've gotten a headache from it many times. And I don't like it. So we put the cover back on. So you don't want to inhale acetonitrile. All right, so protic solvents that are, again, are on this side. The protic solvents can stabilize both a cation and an anion. Now, why would that be? Well, we'll take a look at that. And we'll answer how the properties of polar protic solvents and polar aprotic solvents, how they affect the nucleophilicity of or the strength of a nucleophile. So if we take a look at solvent effects, if you put your nucleophile in a solvent that doesn't stabilize it, okay, it's going to be more reactive, right? Think about a hyperactive child. If you don't find some way to stabilize that child, I was going to say tie him down, but that doesn't sound good, okay? But if you don't find some way to stabilize it, right, it's going to be more reactive, running around and acting crazy. So a nucleophile is the same way. If you want your nucleophile to react, you've got to decrease its stability, okay? So in a polar aprotic solvent, a nucleophile is going to be more reactive, right? This is a nucleophile, so a higher energy nucleophile. The same nucleophile in a polar protic solvent is going to be stabilized, and therefore the activation energy is going to be higher. So the conclusion is that polar aprotic solvents, okay, and aprotic just is the same thing as saying a polar aprotic solvent, are going to be the best solvents for SN2 reactions. So if we go back here, what's a good reaction for an SN2? If you, my friend, are trying to start an SN2 reaction, you'd be best to use one of these solvents. If you're wondering, are there others, Mr. Dion? The answer is absolutely they are, or absolutely there are. Our book seems to be kind of obsessed with these. Well, I don't know. I would just say he uses some more than others. HMPA, I don't think that comes up a whole hell of a lot in this class. Anyhow, and the reason why is shown right here. If you have a polar product solvent that can hydrogen bond, it can stabilize both a cation and an anion. So what does that mean? It means a polar product solvent is going to be able to stabilize the nucleophile, rendering it unreactive. However, if you're in a polar A product solvent, and this is DMSO shown right here, DMSO can stabilize a cation, and there's a picture of it in the textbook, and I'll show it to you on, or I'll draw it out, or we'll talk about it more on, what's today, Wednesday? We'll talk about it on Friday. But if you look at the partial positive charge that is inside DMSO, it's on the sulfur, and it's too sterically hindered to stabilize the nucleophile. And so that is why if you do an SN2 reaction in DMSO, right, your nucleophile is going to be higher energy. It's not stabilized, and it's ready to rock. It's ready to rock and roll, right? Activation energy is going to be very small. If you were to put it in a solvent like methanol or water or acetic acid, then you're going to have a big old high activation energy. All right, and we're going to skip section 7.5, and next class we'll get started around section 7.6.